They are position 1. So perhaps the best approach to this is, instead of trying to match the answer, draw the answer. It's kind of fun. Should we do teamwork all up the boards? Yeah, okay, go for it. So why is it not exactly a 1-for-1? So I'll draw.
I think it is. It's just that I've drawn the.
Because you can draw the carbon structure
here,
differently.
or I could just like flip them and do the same thing.
I drew too many carbons in there.
You still have 2, yeah.
So based off of how long getting to an answer took, I'm going to bet that the very first thing that happened is you looked at the answer choices. Okay. So particularly in a situation like this, should you be able to answer the question without looking at the answer choices?
Yes.
Then don't look at the answer choices. By looking at the answer choices in a system like this, with a question formatted this way, you have immediately set yourself up to be wrong. Because what you're now trying to do is validate why each and every single one of these is correct. They aren't. 3/4 of those answers are wrong. And so by you attempting to validate the question by looking at a wrong answer, you're creating false analogies within the naming system. That's a problem. Stop doing that. Right? This is why when we talk through questions, we try to come up with the answer before we look at the multiple choice. There are certain formats of multiple choice questions. There isn't anything you can do about it. You have to look at the answer choices. Those are always more dangerous than any other question because you're now looking at wrong answers. And one of the things the human brain will try to do is to validate an answer. So the very first answer you read, if it is incorrect, you are attempting to validate it, and you will now create misconceptions in your own brain to screw yourself up and prevent you from seeing the correct answer later in the sequence. So if a question is formatted to allow you to draw out the answer, then flip and draw out the answer. Let's push on that further. The point is to draw out the answer. What's the explanation? Does that look like a drawn out answer, or does that look like a bunch of words?
Bunch of words.
What you're trying to do is validate the answer choice that you've picked, not validate the answer that is correct. Answer the question before you look at answer choices. Again, you can't always do that, but it is to your benefit to do that whenever you can. And if you look at it, you're like, I have no idea what any of those words mean. Yeah, that's a whole different thing. That's a new strategy in taking a multiple choice test. Now you can look at the answer choices and hope by the hand of God something strikes you in the middle of looking at those answer choices that helps you to trigger what you need to know to figure this out. Okay? But if your first approach is hand of God, you've got a problem. Okay? You're setting yourself up to not be as successful as you should. Next question. Actually, no, switch away. Switch back to this. So what do we say the correct answer was? How is D different than the actual answer?
There's no up, down, left, or right, so there is no difference technically.
If there's no difference, why did it take so long to match it to the answer choice? So an individual drawing, yes, you're right. There is no up, down, left, or right. You're responsible for the different permutations. What are the permutations you had to do?
Rotate the carbon chain on the end there.
You had to do a rotation. Okay. This is one of the reasons why it's dangerous to look at the answer choices. Because the answer choices could do a rotation that make you think that you're not looking at a 5-member chain, you're looking at a 4-member chain. 1, 2, 3, 4. Or this one, 1, 2, 3, 4. Oh, I must be wrong because I only have 4 carbons in my chain. A very subtle change in the overall structure can help you invalidate a correct answer. That's why you must draw the correct answer first. That's why a big part of the explanation should be drawing structures. So watch out for how you go through and solve things, because very subtle changes in question format style will break your methodology. Next question. What do you think is the very first complaint? Okay. Fix it. We got boards. Okay. So, I mean, were you given nomenclature rules?
Yes.
Okay. Okay. Were you given nomenclature rules back in Gen Chem? Yeah. Okay. And in doing so, the very first step is to identify the main chain, circle or otherwise mark the longest carbon chain that also includes the highest priority functional group. We kind of got some 1s and 2s and 3s in there, so it's kind of marking. Right? But the whole point of circling is so that you can identify your substituents, the things that are hanging on, so that you know what to name and what else you don't name. Did anybody circle the main chain?
No.
Okay. Okay. So we're not following the rules. Okay. How well is it going not following the rules?
I mean, I think I figured it out. Can't speak for everyone else.
Right? You did figure it out, and well, actually, I don't know, I haven't checked, but let's just assume you did. In 15 minutes, you solved a nomenclature question that theoretically you should have had in less than 30 seconds.
No comment.
And that's fine. Okay? Right now, you're in a homework environment. You should be struggling a little bit and recognizing that you don't know these things, and you should be falling back on the materials that you've been given. And if you're choosing not to use those materials, that's also kind of okay. But what's the repercussion of not falling back on those materials?
Get the question
You're not
out.
gonna get the answer right.
You're going to get a 15-minute lecture from me of why the hell are you not paying me to help you and then not to using my advice. Like, that's a big part of this. Okay? The nomenclature rules and all of that, those individual steps, okay, those are for beginners. Are you beginners? No, you're more advanced, so theoretically those things can start to fall to the wayside. They should start to fall to the wayside when you're getting things consistently right. Were you consistently right? Then you stop throwing things to the wayside if you're not consistently right. There's a reason those guardrails are in place. Okay? If you do bowling, you get bumpers, right? You can pull up the bumpers on it. The bumpers come down when you're consistently making it down the lane. If you're consistently hitting the bumpers as you bounce down the lane to get that strike, you leave the bumpers up. That's how it works. So don't start kicking the bumpers over and being like, oh, I'm ready for this, if your last 5 attempts have all bounced into the bumper walls. Kind of make sense? Okay? And it's fine to use the bumper walls too. Like, come on. Don't be like freaking out over that. Everybody wants to make it down the thing on the path, not in the gutters anyway. Okay? But then the next thing I thought, I just play with for this. So not only do we have the old nomenclature examples, not only do we have explicit examples actually given in lecture content for this thing, but here it is. It shows up right about 10 minutes. 10 minutes into the lecture, just so everybody's aware of this. Okay. And again, YouTube Analytics, I don't know how people pay money for YouTube Analytics because they are very untrustworthy as best as at least God, I hope they're untrustworthy because otherwise it's not reflecting great on viewership. The average view for this video is 9 minutes. So the average view length for watching the content that tells you how to name the ester stops before you learn how to name esters.
Is the video 18 minutes long?
I don't know. Sure. Yes.
Yeah, because we want you sped up.
Yeah.
This
Plus-
and
Oh,
so
really?
and I have no idea how YouTube deals with that. It's 27 minutes.
Oh, well.
So
If you watch on double time, it's only
okay. Which cool, let's address that. Double time. I fully accept that. Is it helping you?
It's helping me not have to
Did
listen
you-
to your voice for an extra 30 minutes.
Cool. Are you getting any of the content right?
Yeah.
So is watching it at double time helping you? We just took the entire class to try and figure out these names. We haven't even looked at the names that are up on the boards yet. Okay? But it took you 15 minutes to come up with those names. This is 2 days before the test. This is go time. This should be 2 minutes, and you're polishing to drop that down to a minute and a half. At most, to come up with the name. And even then, it's naming. Naming is cut and dry. It should be a real fast, I have the answer and I'm done. Okay? Just things to consider and kind of process. Okay? And if you don't consider it and process it, that's also okay, but realize somebody else has to consider and process it, and one of those people would be me. And so I look at it and be like, well, no one wants to listen to what I have to say. Why do I care to make any adjustments on how difficult or easy an exam should be? If you aren't paying attention to anything I have to say, why don't I just rip it? Make it a wicked hard test. Everybody fails. Oh, well, maybe you should try listening to me. Maybe if the test gets harder, you start listening more. I don't think that's true, for the record. Okay? But you have to realize your education is not done yet. It has to continue. There's multiple people involved in this, both you as students and the instructor. And instructors, whether or not they admit it, are affected by student performance. And the people that generally say they aren't and you suspect is because they are so burned out, they don't care how you perform. So they're writing the ripping hard tests. And they're destroying everybody. Well, no one gets it. Well, no one gets it because you're so burnt out and the students are so burnt out that nobody gets through. So when you come up to ask for help, that's great. That's fantastic. Have you spent some of the time to show that you know what's going on with the content? Or are you just letting it wash over you? And both of those are okay. I get it. But they aren't as useful as they could be. And what we're trying to get it through is as useful as it possibly can be for you. I will say the views is, promising. I mean, there's 12 views. We got 9 people in the class. That actually is a number that suggests everybody at least opened the video. Okay, so that's actually a promising number. Believe it or not, this is one of the reasons why I don't like YouTube Analytics. I've opened up several videos. And it's been like, oh, you've had 20 views. There's 30 people in the class. I'm not sure that aligns, okay? Considering that I know several people watch the video multiple times over. Okay, so at least this is a positive indicator. Okay. View time is also a little on the high side. To be honest, I expected more like a minute or two for the average view duration. So wherever my mouse went, there it went. I would say rather promising as far as the views, but we do got to pick up kind of processing out some of this content. So when we go through and deal with esters, we've got a couple big issues that go on. And nearly everybody pointed out some of those issues. Okay? And it's an issue that's going to show up very painfully in spectroscopy as well. If we do a somewhat subtle change, whoops, that would have been a massive change. Somewhat subtle change in the overall structure of our ester. We're looking at the same formula, roughly the same connectivity, except what we've done is swapped, okay, if you will, the directionality of the carbonyl to our ester, so we'll call it pointing that way, versus carbonyl to our ester pointing that way. So we've changed the directionality, be it left to right or right to left. Okay. That subtle change has big implications as far as spectroscopy goes, and it has big implications as far as our name goes. So we have to be able to identify the main chain within our ester. And I keep freaking doing, I think I remembered something. Paste. Boom. Look at that.
You learned it.
Wow.
Can't teach an old dog, something about dogs and
Can teach an old dog.
and where to go to the bathroom. I don't know. Wait, that's not right. Okay. When we go through and look at our esters, that's our ester. That's our ester. This entire chapter was based off of acid derivatives. I don't know how to spell derivative. There's a T and there's a V, there's some F's. A carboxylic acid looks like this, with the H there. Okay? So the derivative is what are we changing ultimately out here? And if we look at the ester, okay, and this gets a little bit weird, particularly with how I've circled it, really what we're changing is not necessarily the H, but the OH. Okay, when we go through and make it an ester, it's an OC or an OR, some kind of carbon structure. Okay, that's our ester functionality. It's better to remember the ester as that switch out than as the H, which is fully acceptable. I understand where you're going with that. But the OC helps to tie back to, man, that's a really bright green up there. Tie back to the mechanism on how esters get made. Okay, the oxygen is coming from the alcohol that comes in and attacks. We're swapping out H versus C. Does that make sense? Okay, so that can help us better understand that. And if we also understand that, that helps us to identify our main chain, albeit I did it a little bit goofy in this particular scenario. Make sense? All right, now that we've identified the main chain, we can go through and name it. Okay? To name the main chain, I would have to have a numbering. Where's the highest priority within that main chain?
I want to say ketone, the carbonyl.
Carbonyl. Okay? And yeah, we have to avoid ketone because ketone implies other pieces, but carbonyl is absolutely it. 1, 2, 3, and in the other case, still 1, 2, 3. Numbering's going opposite directions because of different things. So we're looking at a prop. This is looking at a prop. Okay? Based off of our nomenclature system, we would have to go back to what are esters called. So what is the ending that we get for esters? That's the O8 ending. Whoops. And I should color code that. Okay, and if you're looking at that and being like, propo8 sounds a little stupid, that's because it is. What's the thing that I forgot to include within that? The ane, okay, back to our nomenclature system from OChem 1, the hybridization of our carbons. We're ignoring the carbonyl because that's implied already within the 8. So we've got propan-O8, okay, which my emphasis made it sound weird, but that's fine. Okay. Do I need to specify the location of the ester? No, because by definition, it is at position 1. If there's multiple esters, do I now have to be more specific? Yes, and that's going to open up a whole nother can of worms that we probably don't want to open up. So let's not worry about it. Okay, because we're looking at how do we name things that are at a very high level. Okay? For the most part, what we'll end up calling them is just diesters. This is why when we talk about the malonic ester synthesis, why do we call it the malonic ester? Because we don't know how to name two frickin' esters in the same compound. So we came up with a common name for it to make it easier for us to, instead of having to learn nomenclature rules. It's a bit incorrect, but close enough. The intent is there. Okay? So we don't have to specify the one. If we wanted to, we could. Where could that one show up? It could show up in front of the O8. Absolutely fair game. It can also show up in front of the prop. Okay, why? There's no other functional group listed after from that P afterwards up to the ester, which means the one would apply unambiguously only to the ester. Okay, so both of these get called propanoates. That should be kind of confusing, right? Do they have the same structure? No, but calling them the same name is a bit problematic. Okay, except we have to realize that there's some things that we haven't addressed. Okay, and actually I'm going to color code this piece a little differently. In the structure on the left, we actually have a hanger-on our main chain. Okay? What do we have as that hanger-on? We have a methyl located at position 2. So our main chain is now identified. It looks like you might have been trying to get to it. Yeah, it's okay. We got a 2-methyl propanoate. It looks like you've got it. Sorry, I'm looking at the other structure.
It's propyl 2-methyl.
Yeah, you've got the 2-methyl propanoate core, 2-methyl propanoate core. So good, we've got the cores kind of identified within that. For the structure on the right, we have the main chain already identified. There is no extra piece hanging on the main chain, so it's just propanoate. Okay, but the last thing that we would have to identify is that last hanger-on, okay, the thing in blue. That thing in blue gets split kind of strangely, okay, because you'll note that we wanted the kind of O counted as a separate piece, but that O is what's making it the ester. So by saying O8, we already know the O is there. So really the hanger-on is just out here. So in that first one, what's the hanger-on? It's three carbons. It's just a propyl. Okay, I don't want to call it propane because that ends the name of it. So it's a substituent on that larger piece. This gets obnoxious that is actually shown as a legitimate space. Okay? Which is really hard coming from me as your instructor, because I've never played with spaces appropriately in any of the other names, because we've rarely ever assembled them fully. But when we go through and do esters, that last little piece that's connected to our singly bonded, connected to our oxygen, okay, is a full substituent set out from the rest of the name. Why? You don't want it to get confused with any hangers-on that are on the main chain. So you have to include a space to separate main chain substituents and the last piece that's a substituent.
If there was multiple esters, how would you name that from there? Would it be like
So,
position?
and that's why we said we weren't opening that can of worms.
Okay.
Because, yeah, you start running into issues behind priorities and where those things are, and it gets confusing fast. Okay. What we can try and do is see if we can't look one up and how they go through and name it. So we now have propyl 2-methyl propanoate. That's the first structure. The second structure, that becomes a harder one to name. And this is where people are like, oh, it's got the fishtail, so I want to call it an isopropyl. But it's not an isopropyl, because an isopropyl is this.
So it's an isobutyl?
Okay. If I add that extra carbon, as is done here, I now have 4 carbons with a fishtail, which suggests isobutyl. So we could call this isobutyl as our front piece hanging on. Problem with that is that that is not IUPAC. IUPAC has said that that naming system is too vague and outdated, and we don't want to use it anymore. Does that mean it doesn't get used? No, it gets used all the freaking time. Okay? But you're officially not responsible for it, while simultaneously also being responsible for it, at least based off the past exams I've seen. Okay? Because they'll ask things like, which solvent is protic? And they'll say isopropanol. Like, you're using the iso. You can't do that if you're telling people they aren't allowed to use that as a name. Okay? So how do we name it without using iso? Okay? It's a 1, 2, 3 carbon chain. So absolutely correct. I don't know why I decided a P needed 2 humps. It's a propyl, and it has a methyl connected to it. That methyl is connected at position 2, so I would get 2-methyl-propyl propanoate. And I've now done the full assembly of that name, or that structure, out into a name. Okay? For future reference, you'll note that I numbered that chain starting from where the oxygen was, not say 1, 2, 3. Okay? The propyl is going to come in at position 2 regardless. Which numbering scheme is correct, blue or green? Blue. The green one is incorrect. By definition, your substituents will always connect to the main chain at position 1 of the substituent. So if you have to do a substituent within a substituent, which is technically what's going on here, you have to make sure that you account for your numbering correctly. Is that a bunch of extra rules you don't want to memorize? Yeah? Then guess with nomenclature and move on. Don't worry about it. Okay? Or look at your answer choices and be like, I see isopropyl. I don't think I'm supposed to know that. Eliminate that. It's now not a 25% chance of being right. It's a 33% chance. Okay? Now you can start playing testing games. But when it comes to practice on a practice exam, it shouldn't be testing games. It should be, this is why this is the answer.
Well, I think everybody just got stuck on what to name that hanger-on the ester, to be frank. I think it was less problem identifying the main chain and more identifying how the fuck do we name something that isn't a part of the main chain and all. And that's connected at the ester, not at one of the carbons.
You had a hard time figuring out the name of that.
No, not the name of that. Where to put the name of that?
So what you had a hard time was tracking where's the ester. What defines the ester? Is this the definition of the ester? In which case I should call it propanoate. In this case, it didn't really matter because we had the exact same numbers. Or is the ester here? Red box versus blue box.
Red box.
That seemed to be the problem that I was noticing across the class, is that you didn't know where the ester was. I get it. Okay? A lot of that's just going to come to practice, and that's my fault because how much practice do I give you on nomenclature? Not a lot. Okay? So here you have your first opportunity to practice, so spend some time practicing, and if you can't figure it out, that's okay. You've got a textbook. Okay? I didn't buy the textbook. It's required material, so that's up to you. That's on you if you decide not to. You need to find questions on how to name esters. Your textbook will have tons of questions on how to name esters. The internet will have tons of questions. Make sense? Once you now have the name, you can now go through and match to the correct one within this. And if we go through and look at each of these answers, can we see why it's a bad idea to look at our answer choices to guide our way through? Nearly every single one of those is holding on to some piece of truth with other bits of complete and utter BS. And so trying to name the compound based off of looking at false information is very, very flawed. Okay? We just went through and named this, I would argue, fairly extensively. So theoretically, everybody would look at that last one and be like, that's ludicrous. Why would you answer that? 1, 2, 3, 4, 5, 6 carbons. There's your hex. 1, 2, 3. There's your oxy. Or sorry, not your oxy. There's your own. At position 3, you also have the oxy for like an ethoxy with the methyl now kind of listing pieces off. So there's truth behind all of these. You can find ways to make it appear to be valid. That is the very challenging thing with OChem, is you can almost always validate an answer. There will be parts that you'll be like, but that doesn't make sense. The brain does a really good job of making things that don't make sense disappear from its logic stream. Write them down. Okay, and just because you asked, and I'm vaguely curious now. Diethylmelanate. So diethylpropane dioate. If you were going to have the diester, you're probably going to have the exact same pieces on either end just because of how the ester gets made. But it looks like how you would change it would be a propyl ethyl propane dioate. So you'd have those two pieces out front, be my guess. But yeah, it's going to be effectively trying to break nomenclature. That's what you're trying to do with that. You're trying to create a structure that becomes impossible to name. And then that's where you would come up with the people creating things like this.
Our soul.
You were probably just trying to be an arsehole. Next question. Kind of like me.
For all main practices.
34. Sorry for scrolling if you're watching at home. Cool. So just looking at this question, what do you think? Is this one that you should be able to figure out without looking at the answer choices?
Yeah.
Okay. And I'm not saying can you or do you have the ability or do you know how to do it? I'm just asking, is this something you should be able to do? Yeah. You should be able to completely ignore the answer choices and try and come up with the answer. Okay. So, what do you all see?
See the bromine, bromine, which I mean, I know, I just didn't want to. I didn't know if you wanted to.
Well, okay, so you see bromine. What do you see about bromine?
Well, it'll have a negative and a positive charge because of the two separate bromides, meaning that one can act as a base while the other one acts as as an electrophile. Thank you.
Is that going to ever happen?
No,
Why not?
this bromide only likes one bond.
And I hate to be the bearer. I'm always the bearer of bad news, so I'm used to it by now. But we will see scenarios where we can form, and we've already seen scenarios this semester with bromine with more than one bond. Okay, but it's a rare scenario to pick up. So generally speaking, we should only see a bromine with one bond. That screams problematic to us.
We saw something just the other day on the homework that was just like this. But continue.
Okay, yeah, you probably did. So if this reaction isn't going to happen, does Br2 act as a base? No, it does not. Okay, so it's the part that I really, really want to call out. You see bromine, fantastic, great. It has a positive and a negative. Objection. When you see bromine, what do you see?
Leaving group?
You see a leaving group. Fully accept. Yes, lovely. That's fantastic. And if I see a leaving group, what does that mean this side is?
Fuck. This is the
This
exact
is what-
same,
this is
almost
what?
the exact same thing I said. The exact thing that
It's
I said.
not even remotely close.
I'm telling you. There'll be electrifying.
This is now positively charged. Okay? So when we look at bromine, elemental bromine, it's an electrophile. It's positive. There is no negative. Period.
But wouldn't there be a negative bromide? If that bromide leaves, it would be a positive.
After the reaction has happened, do I have a bromide? Yeah, after a reaction has happened, I now have a nucleophile. Great. After it has happened.
Oh,
Okay. Am I dead? Because if I got shot, I'd be dead. Does that make me dead right now? No. Okay. Evaluate the current scenario. The current scenario is that bromine, elemental bromine, is positively charged. It's an electrophile. Okay. And it's stupid hard to remember that because you every time we see bromide, oh, it's electron, it's electron. Elemental bromine is positively charged, period. That's all it is. Don't make it negative. It is not negative. It will never act as a negative. Elemental bromine is positive, period. What about elemental chlorine? Yeah, it's the same thing. Yeah. Elemental iodine.
Same thing.
Right? They are all electrophiles, and that is all they are. After a chemical reaction happens, you've produced side products. Those side products happen to have a similar name, right? It's bromide. Okay, we changed the name. You changed the name, you changed the chemistry. Yes, absolutely. But just because they have the same core name, don't start swapping that chemistry back on it. Okay, make sense? Okay, it's insanely hard to do. I'm fully aware of that, but be aware of that issue. Okay, because you will absolutely get things setting up where you're trying to turn elemental bromine into a nucleophile. Don't do it. Elemental bromine is an electrophile. Okay, so cool. You see the bromine as a potential positive. We'll put a little positive above it. What else do you see?
PCl3.
Okay, what do you see in PCl3?
As odd as it sounds, we replaced the alcohol on the carbonyl.
Okay, cool. So what's now happening is you see this next reagent, and instead of saying what its chemistry is, which is fine, okay, but what you're doing is you see that reagent, and you're now saying these things together take an OH and turn it into a bromine. That's lovely. Different level, because you've now memorized some piece of that chemistry. That's good. So what does that suggest needs to be in the box? You need an OH. Okay? I want to touch on some language here. Okay? We had one person repeat, we need an OH. I need to see an OH in the box, and I had another person say, we need an alcohol. Is an alcohol the same thing as an OH? No, they are very, very different conclusions. Because the OH could be connected to an alkene, in which case it's a ketone. And we've got a ketoenol tautomerization. Yay! Okay. Or the OH could be connected to a carbonyl, in which case it's a carboxylic acid. Very different chemistry. Okay. So we want to be kind of cognizant of all of that kind of information and be careful to not add more information than we know. At this point, all we know is that there's an OH. Could it be an alcohol? Yeah. But I don't know. Okay? So now what happens?
That water would come in and, well, I would just replace it again? What the fuck is the point of that? Doesn't make any sense.
Okay, that's fine. So you see the water, and again, what you're now jumping to is what that means as a conclusion, that the OH would then do a chemical reaction, or the water would do a chemical reaction. Okay, this is a case where I would step back and say, well, what are you saying the water acts as?
A nucleophile.
Okay, you're saying it acts as a nucleophile, and as a nucleophile, it would go through and potentially convert the bromine that we produced in the previous step back into an OH.
That's recreating a carboxylic acid.
Yeah, that sounds pretty sus. Okay, I mean, that's possible, but you know, that's a little weird. Okay, and then what is step 3 supposed to do? What does step 3 supply?
Nitrogen.
H+.
A nitrogen, and how does the nitrogen act? It acts as a decent nucleophile. We've got the presence of our H+. Okay, that H+, depending on our conditions, could maybe supply our H out here. Okay. So now we've got to kind of process through some of this. We know we have an OH in our starting box. Okay, do we know anything else that belongs in that starting box?
I mean, the core carbon structure, because that can change based off
Why? Yeah. Finish your statement. Yes.
based off the reagents, it can change.
Based off the reagents that we've listed, we don't expect any carbon structure change. So the carbon skeleton should stay constant. Whatever's in that purple box should keep that core carbon structure. Okay? And we know we have the OH out there. So if we ran this chemistry, we would turn the OH into a bromine, we'd then turn the bromine into an OH, and then we would add a nucleophile that probably wouldn't do anything. Right? Okay. We know that somehow something needs to happen with a carbonyl here, right? And we also know somehow we have to bring in the nitrogen here. I don't know why I didn't make a large circle again, but
Well, nitrogen's negative, typically. So something positive there, or something that would create a positive charge at that carbon.
cool. It would be nice if we had had some functionality here, okay, at some point, because we run reaction 1 to produce a material, we run reaction 2 to produce a material, and we run reaction 3 to produce our final product, right? So at some point through this system, I need in that orange thing, what? Ooh, that was a weird...
Carbocation.
Okay.
Leaving group.
A leaving group at some point. Okay. What would be a good leaving group?
Bromine.
Bromine would be a good leaving group. Do I react the structure in a way that would produce bromine?
Yeah.
I do indeed, actually. Okay. That very first step tends to bring in bromine, right?
This is exactly what I thought would happen, but I was like, then what the fuck acts as the base?
Okay. So I don't understand. Does everybody else understand what he's trying? Okay. So this is exactly what you think would happen. Okay. So give me some more.
So this alpha hydrogen, something will take the the hydrogen off, would leave in the electron, so that bromide would electrophilic bromide would come in and.
So you're saying that we have hydrogens here.
That
and
are
if-
somewhat acidic
Why are they somewhat acidic?
due to its it being alpha to a carbonyl.
Alpha to a carbonyl. I love that, except in our purple box, do we have a carbonyl yet? No. So you're suggesting in that red section, that red dotted line,
A carbonyl.
I'd better have a carbonyl so that that alpha position is now active and chemically reactive. Okay? So if I added a base, what would the base do?
It would depronate the carboxylic acid.
Okay? So yes, we have that alpha position. Yes, we could try and make chemistry happen there. That's the old school chemistry that we would love to have happen. Except I have a carboxylic acid, and what would the carboxylic acid do? It would deprotonate the base. I've got nothing now to remove that enolizable hydrogen. Turns out that it's not enolizable. Carboxylates have resonance stabilization of the carbonyl, so much so that I can't enolize that hydrogen. So that would suggest I don't want a carboxylic acid. What would be a different functional group that I could put there?
The one with the halophore?
How about we convert the OH into a bromine? To do that, what reagent would we need? PCl3. And if I did PCl3, whoops, that should get rid of the OH and now replace me with either a chlorine or bromine, depending on how you want it. Believe it or not, they did PCl3 instead of BR3 as a hint. Why is BR2 present?
Maybe to stabilize the intermediate.
What's special about this structure? Or rather, what problem does it not suffer from?
Steric hindrance.
That was, nope, shouldn't have done that. That the previous structure did suffer from.
Oh, the highly acidic functional group.
Okay. The alpha hydrogen is actually now very acidic. So much acidic that what can happen?
And now
It can tautomerize on its own. And if it tautomerizes, what does it create? What does it create?
the negative carbon,
Why would a negative carbon be useful?
the electrophilic bromide.
You mean the elemental bromine that was now floating around in solutions? So that nucleophile can go through connect, and we now have chemistry at our alpha position. Cool. We then add water. What's the water going to do?
Replace that Cl with an OH or just an O.
Replace the Cl with the OH like gangbusters, because that's an insanely reactive functional group.
Gangbusters?
Fine, I'm old. Is that an old saying?
What the fuck is gangbusters?
I don't know. Don't ask me to explain slang from 20 years ago, 30 years ago, however many years ago. Okay? Now what happens?
The bromide leaves, and then the nitrogen comes in, and it effectively ejects the hydrogen. Did that give you the NH2? If that makes any sense?
And then we'd set up with our final product. Are we going to have some weird protonation states with this? Yeah, because it's freaking nitrogen, and nobody thinks it's nitrogen through cleanly. You shouldn't hate it, just realize that nobody draws it correctly.
I hate mercury more.
I mean, uranium's
You can't
kind of
say
up
you
there.
don't hate a specific element.
They all have their uses.
Oh, you have nine mercury.
Okay, so what does that mean? What did we start with?
Well, I mean, isn't that just that thing?
Yeah. That thing right there at the start. So we needle through what information we've got, what stuff we had to process. Okay, deciding whether it was an alcohol or a carboxylic acid had to come back to what we saw, and ultimately in this case what Anthony saw, and I just kind of assumed the rest of everybody else saw, is that to get that hydrogen to be acidic so that it could act as a nucleophile or an electrophile even, okay, we had to get rid of a hydrogen. Once we've identified that removal, it has to be acidic somehow. If it was next to a carbonyl, that would work. Bingo, we bring the carbonyl from the end back to the beginning. And we say, well, then how would that work? It's not enolizable because it's a carboxylic acid, and carboxylic acids aren't enolizable hydrogens. That now sets us up to be able to see that whole pattern. Does this question take a lot of time? Yeah, I think it does. This is why that nomenclature question should have taken. That's a bit excessive,
I was exaggerating.
but I get it. Okay? That's why when you see those nomenclature questions, those should either be just a gift, yep, I know the answer and I can figure this out real fast, or I fully understand that I have not done anything with nomenclature and it's equally a gift because you can guess and move on. You don't have to think about it. You've already acknowledged that you don't know it and you can advance. Both of those are good things. You leverage them. I feel you. Does that make sense?
Well, I think I was just confused with how the BR2, the mechanism behind it. I knew what it was going to do, but I just didn't understand how it was going to do it, I suppose.
Yeah. Some of that, what I think boils down to, would be, actually, I'm circling kind of the wrong thing, would be that system calling out at the very beginning. Is that hydrogen enolizable? Okay, and that's a real hard thing to acknowledge and to know kind of offhand. To that end, where's the question?
Oh, shit.
Question 32. Which of the following does not contain enolizable hydrogens? You mean there was another question that was answering a little bit of information that could have provided context to help you solve a harder question? Huh.
So C.
Somebody was attempting to look out for you a little bit, give you a little bit of information in a different spot, in a different format that could have helped jog you back on track. This is why it can be powerful to read the entire exam. Sometimes it's explicit. We can listen to the recordings. I'm always explicit. Okay. Other times it's someone just made a mistake and they wrote a question that helps another question later on in the test or earlier in the test. So just be aware of those contexts. They can help you. They can. Not always, but they can. So yes, in this case, it's C. Okay, and just because we're here, let's lean on this explanation. The oxygen is the most acidic, so we cannot enolize I'm just going to pretend that wasn't there. And just say we cannot enolize. Dumb thing. Everybody's favorite word. Excess OH minus. Oxygen on the hydrogen is the most acidic, so it removes it. Now I have excess hydroxide. With this explanation, I would argue, why can't that excess hydroxide remove the alpha hydrogen? Acting as a nucleophile is just going to regenerate the carboxylic acid at best, which is then just going to get deprotonated again by the base, and you're going to go through a never-ending cycle that doesn't remove base or add base.
Honestly, I don't see any reason why it wouldn't be able to take on that.
The conjugate base is the carboxylate, which is incredibly resonance stabilized. It just won't allow the resonance of the enoling to happen at all.
The whole ability on removing that hydrogen is because it is resonance stabilized. And if we go through and look at the carboxylate is very preoccupying that resonance ability, which effectively means that group is non-existent to the negative carbon. Can the negative carbon do any resonance? Okay. So when we're talking about the enolizable hydrogens, we have to be aware of what hydrogens we're removing in each of those cases. Everyone, were you going the same kind of path? I saw your hand up the same as hers. Yeah. So,
there's a limited amount of resonance that can take place, even though even the forms that should be able to resonate
so
are
it's
so long.
competing resonance. So, and this comes into that line, right? If we're looking at an alpha beta unsaturated ketone, right? Okay. In this structure, we have two electrophilic sites, right? Where does the Grignard attack?
B.
A.
You're right, 'cause it's connected to oxygen. Okay.
Okay, so a Grignard, negative carbon, attacks A. How about a Gilman, also negative carbon? Where does it attack? B, good job. So it attaches at a different spot, right? How do you know that? Okay, which is fine. Okay, at some point you have to memorize. There's a break. Okay, another negative carbon. You ready? Negative carbon enolate. Where does it attack? A and B. Okay. So to your question of, well, when's that resonance? You're right. There is a line that gets crossed. And as soon as that line is crossed, we lose some of that ability. How much ability we've lost is ultimately going to depend on the actual experimental result, and we would have to know the experimental result. Same thing happened when we looked at negative carbons. Grignards to Gilmans, we're oscillating that chemistry between kinetic and thermodynamic. How do we know when that line's been crossed? Right now, the only way we know is because someone has tested it and told us the answer. Which, if you're listening and you're like, well, dang, that's kind of a bullshit answer. Yeah, I completely agree. Okay. There might be some theories out there that help to explain that better and look at the raw energetics behind those systems. That now starts to move outside the scope of the class. And by starts to, it's light years ahead of it. Okay. So that could be something that you could study potentially even for a PhD, because I don't know if anybody's actually looked at that or not. And I think that's one of the problems if you think about using AI even to try and predict chemical reactions, is it's going to be limited by what it was trained on. And what an AI model might be able to do is come up with the theories on where that line is. Whether or not it's accurate or not, I don't know. Sorry, I've got AI on the brain apparently. Make sense? Cool. We're officially done. Sorry.